One of the brightest scientists ever to live on the Earth was Professor Stephen Hawking. His legacy still looms large even after his demise because of his numerous contributions to astronomy and science in general. Many of Hawking's brilliant theories are still being proven posthumously despite some other scientists opposing them. One of the theories which will finally be proven right now that scientists have the adequate tool is his black hole theory. The new equipment is the powerful James Webb Space Telescope just launched by NASA. How will the JWST finally prove Stephen Hawking's black hole theory? Stay tuned to this video to find out. The universe is full of scary objects, but black holes are among the scariest. While they may be exaggerated in sci-fi flicks, the truth is that they are frightening, and as you shall soon see, you better avoid black holes like the plague. But what exactly are black holes, and where do they come from? There is one common conception about black holes, and it's due to the name. When people hear black holes, they imagine a hole that is pitch black. However, technically, a black hole is empty space. But of course, there is much more to black holes than just empty space. A black hole is a great amount of matter packed tightly into a very small area. You can imagine a star 10 times more massive than the Sun, squeezed into a sphere approximately the diameter of New York City. The outcome is a gravitational field so strong that nothing can escape from it. In fact, not even light can escape from a black hole. Scientists have been pushing around the idea of an object in space so massive and dense that light could not escape it for centuries. The most famous ideas about black holes were predicted by Einstein's theory of general relativity. The theory seeks to establish that when a massive star dies, it leaves behind a small, dense remnant core. If the core's mass is more than about 3 times the mass of the Sun, the equations show that the force of gravity overwhelms all other forces and produces a black hole. So how do you detect a black hole? Since they do not emit light, you can't just point your telescope in the direction of a black hole and capture its image. In fact, scientists can't directly observe black holes with telescopes that detect X-rays, light, or other forms of electromagnetic radiation. However, they improvise and infer the presence of black holes by watching out for their effect on other matter nearby. For example, if a black hole passes through a cloud of interstellar matter, it will pull matter to it. This process is known as accretion. Something similar occurs when a normal star strays close to a black hole. In this case, the black hole can tear the star apart as it pulls it toward itself. As the attracted matter accelerates and heats up, it emits X-rays that radiate into space. Scientists recently discovered evidence that black holes have a dramatic influence on the neighborhoods around them by emitting powerful gamma-ray bursts, consuming nearby stars and spurring the growth of new stars in some areas while stalling it in others. You really don't want a black hole in your backyard. So where do black holes come from? Black holes actually represent a transition. They form when stars die. Most black holes are created from the remains of a large star that gave up the ghost in a supernova explosion. When smaller stars die, they become dense neutron stars, and they are not massive enough to trap light. But if the total mass of the star is large enough, or about 3 times the mass of the Sun, it can be proven theoretically that no force can keep the star from collapsing under the influence of gravity. However, as the star collapses, a strange thing that may be difficult to conceptualize starts to take place. As the surface of the star nears an imaginary surface called the event horizon, time on the star slows relative to the time kept by you as an observer that is located far away. When the surface reaches the event horizon, time stands still and the star can collapse no more. It becomes a frozen, collapsing object. Frighteningly, bigger black holes can form when 2 smaller black holes combine in stellar collisions. You can also get a bigger black hole when a black hole and a neutron star collide. One of the things that puzzle scientists about black holes is the scale of the sizes. You either have a huge black hole or a small black hole. Mind you, small here is relative. However, on the one hand, there are countless black holes that are the remnants of massive stars. These stellar mass black holes are usually 10 to 24 times as large as the Sun. Judging from the number of stars large enough to produce such black holes, however, scientists estimate that there are as many as 10 million to a billion such black holes in the Milky Way alone. On the other end of the size spectrum are the supergiants known as supermassive black holes. They are millions, if not billions of times larger than the Sun. Astronomers believe that supermassive black holes lie at the center of virtually all large galaxies, even our own Milky Way. Astronomers can detect them by watching for their effects on nearby stars and gas. Stephen Hawking talked about black holes in his lifetime, and it was always informative listening to his lectures that covered these massive celestial objects. You can find some of these lectures on YouTube. However, some of his theories could not be tested or confirmed due to a lack of necessary equipment. However, a single scientific instrument is changing this. The new James Webb Space Telescope is here to help scientists delve into the mind of the late Hawking and finally confirm his theory about black holes. The JWST is a marvel of engineering and evidence of what humans can achieve when they work toward a common goal. Many space telescopes have been launched and are serving us, but the JWST is in a class of its own. It comes with a hefty bill along with a strong dose of risks. The Space Observatory cost a whopping $10 billion and was developed by NASA in conjunction with the European Space Agency and Canadian Space Agency. It also got input from more than 300 universities. The result is the most powerful telescope ever built, overshadowing the Hubble, which has served us faithfully for decades. Thanks to a successful and precise launch, NASA announced that the JWST should have enough fuel to more than double its minimum mission life expectancy of 10 years. Since its launch, the James Webb Space Telescope's accomplishments just keep on coming. The JWST traveled more than 1 million miles before reaching its orbit around the Sun, where it will permanently reside. It successfully unfurled its delicate and massive 5-layer sunshield and giant main mirror in transit. The two parts had to be folded to fit on the launch vehicle. The telescope is now close to going into full operation after NASA had calibrated and fine-tuned it. There was lots of excitement when NASA announced that the James Webb Space Telescope had captured its first images of starlight. The first image taken by Webb was of a star called HD 84406. Light from HD 84406 was captured by Webb's 18 mirror segments located on the primary mirror, resulting in a mosaic of 18 scattered bright dots. NASA later released a new and improved image of HD 84406, which brought 18 unfocused copies of a star into a deliberate hexagonal formation. Once the observatory has successfully aligned the individual segments of the primary mirror, it will begin the image stacking process. This will bring 18 images on top of each other into one clear view. Thanks to its sophisticated parts, the JWST will help scientists investigate the early stages of the universe after the Big Bang started the universe as we know it today. It will study what happened after the first stars formed. This era is called the epoch of reionization because it refers to when neutral hydrogen was reionized, that is, made to have an electric charge again by radiation from these first stars. This involves looking back billions of years. It will also help scientists to discover exoplanets, which are very difficult to spot because of the way they interact with their host stars. The new telescope will hunt for evidence of life on these faraway planets. Its powerful sensors will be able to observe these planets in more depth, including in some cases imaging their atmospheres. Understanding the atmospheres and the formation conditions for planets could help scientists better predict if certain planets are habitable or not. This is apart from studying the assembly of galaxies. Scientists study galaxies to see how matter is organized on gigantic scales. This in turn lets us see how the universe evolved. The spiral and elliptical galaxies that you see today did evolve from different shapes over billions of years. So one of JWST's goals is to look back at the earliest galaxies to better understand that evolution. Scientists are also trying to figure out how we got the variety of galaxies that are visible today and the current ways that galaxies form and assemble. However, most importantly, the JWST will attempt to verify Hawking's controversial theory about dark matter. But what exactly is dark matter? As the name implies, dark matter is material that scientists cannot observe because they do not emit light or energy. So if you are near dark matter, you won't even know it because you can't see it. However, scientists are sure it is there. In fact, they claim about 80% of the universe's mass is made up of dark matter. It just floats around being massive, affecting the gravity within galaxies. It is tempting to think that black holes might be responsible for this elusive stuff. You know black holes are dark as mentioned earlier, so filling a galaxy with black holes could theoretically explain all the observations of dark matter. Unfortunately, there is a problem with that theory. In the modern universe, black holes form only after massive stars die, then collapse under the weight of their own gravity. So making black holes requires many stars, which involves a bunch of normal matter. Scientists know how much ordinary matter is in the universe from calculations of the early universe, where the first hydrogen and helium formed, and there simply isn't enough ordinary matter to make all the dark matter astronomers have observed. Hawking tried to solve this puzzle with a theory of his own. In 1971, He suggested the black holes formed in the chaotic environment of the earliest moments of the Big Bang. There, pockets of matter could spontaneously reach the densities needed to make black holes, flooding the cosmos with them well before the first stars twinkled. Hawking suggested that these primordial black holes might be responsible for dark matter. While the idea was interesting, most astrophysicists focused instead on finding a new subatomic particle to explain dark matter. Hawking's theory also had its problem, and the primordial black hole formation models ran into observational issues. For one, if too many formed in the early universe, they changed the picture of the leftover radiation from the early universe known as the cosmic microwave background, or CMB. That meant the theory only worked when the number and size of ancient black holes were pretty limited, or it would conflict with measurements of the CMB. Scientists worldwide have been observing Sagittarius A, the supermassive black hole at the center of the Milky Way galaxy. They know the black hole exists, evidenced by its gravitational effects, but imaging it has proven elusive. Sagittarius A won't be the first black hole to be imaged. In April 2019, a group of more than 200 astronomers from all over the world unveiled the very first image of a black hole. They used the Event Horizon Telescope, or EHT, an array of radio telescopes to image the black hole at the center of the galaxy Messier 87, or M87. The EHT team compiled the image from 8 telescopes on 5 continents, working over an observing period of 7 days. M87 is located about 55 million light-years from Earth and weighs in at about 6.5 billion times the mass of the Sun, much larger than Sagittarius A. However, scientists are more interested in Sagittarius A being the center of our galaxy. The JWST will now spearhead the effort to image this black hole. It is located about 27,000 light-years from us and is 4 million times the mass of the Sun. So what makes Sagittarius A challenging to image, even though it is closer to us and smaller than M87? Well, the first image of a black hole revealed the silhouette of the black hole surrounded by a glowing halo of fiery gas. Nicknamed a ring of fire, the hot gas formed a circular shape around the black hole's event horizon. In the process, it confirmed predictions of what a supermassive black hole looks like. However, the view of Sagittarius A is also distorted by plasma, or cloudy ionized gas, that stands in the way between ground-based telescopes and the black hole as they look through the plane of the Milky Way galaxy. Sagittarius A also has flickering flares in the material surrounding it, which alter the pattern of light on an hourly basis. Sagittarius A is the only known supermassive black hole to have this kind of flare. While that has made capturing an image of the region very difficult, it also makes Sagittarius A even more scientifically interesting. The JWST is our best shot at uncovering the secrets of Sagittarius A. Apart from its powerful capabilities, the telescope is positioned in such a way that will give it an uninterrupted view of Sagittarius A throughout its cycles of flaring and calm. That's because, as stated earlier, the JWST will be occupying a position 1 million miles away from Earth at the Lagrangian point 2 gravitationally stable point. The L2 orbit is just perfect because it ensures that the telescope can stay facing away from the Sun at all points, protecting itself against the light and heat of the star. JWST's orbit also keeps the telescope out of the shadows of both the Earth and Moon, allowing it to have an unobstructed view of the universe for the entire duration of its orbit. In contrast, the Hubble Space Telescope goes in and out of the Earth's shadow every 90 minutes, affecting its output. Using multi-wavelength observations of Sagittarius A by EHT, Webb, and other telescopes will help scientists better understand the mechanisms that govern these cosmic beasts. One of the things that scientists want to understand about Sagittarius A is what sparks its flares, how they peak and later dissipate. This not only helps scientists study black holes, but it will also give them better insight into the Sun and its flares. However, scientists returned to Hawking's theory in 2015 when the Laser Interferometer Gravitational Wave Observatory found its first pair of colliding black holes. The two black holes were much larger than expected, and one reasonable way to explain their large mass was to say they formed in the early universe, not in the hearts of dying stars. In their research, Priyanvada Natarajan, Nico Capilouti of the University of Miami, and Gunther Hassinger of the European Space Agency did more investigation into the theory of primordial black holes, exploring how they might explain the dark matter and possibly resolve other cosmological challenges. To pass current observational tests, primordial black holes have to be within a specific mass range. The researchers made several assumptions, including that the primordial black holes had a mass of around 1.4 times the mass of the Sun. They constructed a model of the universe that replaced all the dark matter with these relatively light black holes, and then they looked for observational clues that could validate or rule out the model. The team discovered primordial black holes could play a significant role in the universe by seeding the first stars, the first galaxies, and the first supermassive black holes, or SMBHs. Observations indicate that stars, galaxies, and SMBHs appear very quickly in cosmological history, perhaps too fast to be accounted for by the process of formation and growth that we observe in the present-day universe. These scientists theorized that if primordial black holes exist, they could well be the seeds from which all supermassive black holes form, including the one at the center of the Milky Way. This theory is simple and doesn't require a zoo of new particles to explain dark matter. According to Capelluti, our study shows that without introducing new particles or new physics, we can solve mysteries of modern cosmology, from the nature of dark matter itself to the origin of supermassive black holes. Natarajan said in a statement about this slightly modified version of Hawking's theory, "What I find personally super exciting about this idea is how it elegantly unifies the two really challenging problems that I work on, that of probing the nature of dark matter and the formation and growth of black holes, and resolves them in one fell swoop. This idea is only a model, but it could be tested relatively soon. The JWST is specifically designed to answer questions about the origins of stars and galaxies, and the next generation of gravitational wave detectors, especially the Laser Interferometer Space Antenna, or LISA, is poised to reveal much more about black holes, including primordial ones if they exist. Together, the two observatories should give astronomers enough information to piece together the story of the first stars and potentially the origins of dark matter. What is the truth about black holes, and how big can they get? The second biggest supermassive black hole in the universe is the Holmberg 15A black hole. Holmberg 15A is a supergiant elliptical galaxy located in the center of a group of over 500 galaxies called Abell 85, located about 716 million light-years away. The black hole was discovered by a team of astronomers at the Max Planck Institute for Extraterrestrial Physics and University Observatory, Munich. So how large is the black hole in Holmberg 15A? This monstrous black hole is the equivalent of 40 billion solar masses, which is about 2% of the mass of the entire galaxy. This black hole was most likely formed as the result of a long series of galactic mergers. The prevailing theory, supported by numerous hydrodynamic simulations, predicts that in the merging between two galaxies, their central supermassive black holes, or SMBHs for short, sink gradually towards the center of the new galaxy resulting from the merging. The two SMBHs attract each other by mutual gravity, thus forming a binary system, whose orbit, at first very wide, gradually narrows as a result of energy exchanges with the myriad of stars that populate the core of the new galaxy. The dynamics of these gravitational interactions between stars and black holes are such that, at each encounter, the two SMBHs cede part of their orbital energy to the stars that pass in their vicinity. As a result, the orbit of the two black holes becomes gradually narrower, while grazing stars end up ejected at high speed outside the galactic core on mostly radial orbits. Thus, over millions of years, the center of the galaxy gradually empties of its stars, which explains the luminosity deficit observed in Holmberg 15A and other elliptical galaxies. The title of largest ever black hole goes to the TUN 618. It is a hyperluminous quasar located 10.37 billion light-years from Earth. It contains the biggest black hole known to mankind, weighing 66 billion times the mass of our Sun. It was first discovered in 1957 while surveying faint blue stars that do not lie on the Milky Way plane. A more detailed radio survey conducted in 1970 identified TUN 618 as a quasar. TUN 618 is considered an accretion disk of extremely hot gas swirling around the massive black hole in the galaxy's center. It is so bright that it outshines the rest of the galaxy. It is one of the brightest objects in the universe with a luminosity of 4 by 10 to the 40 watts, which is equivalent to 140 billion times the Sun's. The emission lines in the spectrum of Ton 618 indicate that the gas is traveling very fast, with hints of 7,000 kilometers per second speeds of infalling materials, indicating a very strong gravitational force. It is from this measure that the mass of the central black hole of Ton 618 is estimated to be at least 66 billion solar masses. This is considered one of the highest masses ever recorded for such an object, higher than the mass of all stars in the Milky Way galaxy combined, or 15,300 times more massive than Sagittarius A star, the Milky Way's central black hole. In fact, with such a high mass, Ton 618 may fall into a proposed new classification of ultramassive black holes. Black holes in this category have a Schwarzschild radius of 1,300 astronomical units, or about 390 billion kilometers in diameter, which is more than 40 times the distance from Neptune, the last planet in the solar system, to the Sun. Let's hear what you think of black holes in the comments section below.